Wow. Everyone's so obedient.
And quiet.
I'm amazed. Yes, test. Yeah, it's good. All right, so this session is going to be mostly Daniela telling you about awesome things you can do to analyze data once you have it. But first, I'm going to take about 5 or 10 minutes and go through how you actually, the various ways you would actually get data into Python so you can start doing things with it, right? All right. So one type of data you might have is what's known as CSV, or column separated values, or comma or character separated values. So there's a lot of different ways to read this into Python. So this first block here, this is a whole bunch of stuff just to actually get some CSV data so I can demo it. And this is actually also useful if you want to take a look at this for an example of how to run an SQL query on SDSS data. So you can look at this notebook in the repository. But basically, I'm just doing this query and then saving it to a CSV file.
Is requests the thing that's getting the SQL interface?
No, requests is just doing the HTTP query. Yeah. So requests, there's a built-in module in Python called URLlib. Request is like an external one with a nicer interface. It's like just easier to use. So if you look at the CSV file that I downloaded, it's 74K. And if you look at it, it looks like this. Okay, bunch of values separated by, how do I kill this? Stop. Separated by commas. So the most basic way to do this probably is to use numpy.loadText. So to do this, you need to tell NumPy what the values, or what types the values are in all these columns. So it's a little bit verbose. So here I've got to go and look, all right, I know my CSV file contains these different column names, and I've got to specify for each one what the data type is. So most of them are floating point. There's a class in there that's a string, so I've got to tell it it's a string, and I've got to tell it how many characters it is. And then finally, you can call numpy to load text, and also I've got to tell it to skip some rows because there's some comments, and then pass this data type list as the dtype parameter. And it finally works. But it is, and you can see that I've got this numpy, called a numpy structured array, which is a array with multiple different types of data in it. So you can see they're mostly floats, but I've got some string values in there. It's all kind of verbose to do this. Yeah?
I frequently use save text and load text, but they're quite slow. Do you have anything to say about an alternative thing?
Yes. I recommend using. Oh, sorry. Yeah. Sorry. Yeah. We should be repeating all these questions, and I'm going to forget again, so tell me again. So the question was, load text and save text in NumPy are pretty slow, which can be an issue if you're dealing with any sizable amount of data. Yeah, so alternatives for CSV type readers are a couple of things I'm going to talk about that are both faster. Yes, binary is the true answer. All right, so yeah, it's kind of verbose to do this. It would be nice if it could actually figure out the data types for you. So one option for doing this is to use in AstroPy. In the I/O module, there's an ASCII submodule, and with this, you can take the same file and just do ASCII.read and tell it that it's CSV format, and you can even tell it what the comments are, and it will find them. So when you do this, it will get an error because I didn't import it. All right, so that worked. And what is data? It's not a NumPy structured array. It's an AstroPy table. And I'm not going to go into that, but it's basically like a nice interface that has stuff like pretty printing itself when it's in an IPython notebook. But you can see that it inferred all the types of the columns for you. It figured out that this is a string. And by the way, the reader is actually quite fast. It was improved in the last year. So this is a pretty good way to go, especially if you already have AstroPy. Another alternative is pandas. If you want to work with pandas, you can do a pretty similar thing here. There's a read CSV function. This will give you back, of course, not an AstroPy table, but a pandas data frame, which is kind of the same idea. It's a collection of columns, and it's done all the same stuff, like figuring out all the data types for you. We obviously don't have time to go into pandas, but you can do stuff like .head, and it'll show you the first 5. You can do stuff like .describe, and it will calculate some statistics for you. Pandas it's a huge library with a lot of functionality. And besides CSV formats, it can read from all sorts of different formats. So even Excel. I have no idea what FWF is. Yeah, so it has a lot in there, especially for I/O. Yeah? I think they're similar now in terms of the I/O speed. I think for like once you're actually doing operations on them, they're both using NumPy under the hood. But yeah, for a while, Panda's CSV reader was like the benchmark fastest CSV reader out there. All right, so but astronomy, we often have some weird text format files. So for example, data published in AppJ and AJ are in this like weird CDS format that has a README describing the format and then the actual table in a separate file. AstroPy has stuff to read this, so this block is just getting that data. The data table looks like this with no header. It's just the values. So you need, and then the README is this long, terrible thing that's has a header, and then finally somewhere down here describes the actual bytes in the data. So you definitely don't want to like write a parser for this. So you can use stuff in AstroPy to do this. You just tell it what the format is, and then tell it where to find the README, and it will parse that whole thing and figure it out and give you back a nice table with all the contents. And it actually even knows the masking. So it knows these are masked values, the ones that are missing up in the original file that were blank. There's some other astronomy-specific formats in ASCII. So if there's some file you have that has some weird format, I would look there first. Yeah, so you can go to this is a link to the documentation with all those supported formats. So Fitz Files. We all love Fitz Files or hate them, whichever. Love-hate relationship. This block is just grabbing a data from a file from SDSS just as an example. So you've kind of got two options for reading Fitz files in Python. One of them is astropy.io.fitz, which used to be pyfitz. And just to give a quick demo of this, you can import it like this and then call fitz.open. It will give you back an HDU list because Fitz files they're basically like blocks of header data units. And so in AstroPy, it's represented as just a list of these things. You can ask the list for some information, actually. It's not actually a Python list. It's just something that kind of looks like a list. So it has this .info method. And it'll kind of give you a summary of everything. And then to actually get the data or header out of each individual HDU, you would index it and say, so this is saying, give me the data of the first HDU. And so that actually reads in the data. And then similarly with the header.
But it doesn't read it until you ask?
I'm pretty sure it doesn't read it until you actually call this .data. An alternative that you might be interested in if you're like really I/O limited is this FitzIO library. It's not quite as easy to install. It's not on Conda. You have to have a C compiler and pip install, but it should work. It is faster, particularly for tables. And I was finding lately that it does a better job with ASCII tables if you are unfortunate enough to have to deal with those. So this is pretty similar. You create this Fitz object. If you just print it, it will tell you a smaller summary of what's in the file. If you index into it, it will tell you a summary of what's in the first HTU only, like what the data type is and how big the image is. Similarly for tables. And then to actually read the data, you call a .read method, which is kind of nicer because it's a little more explicit about when the data is being read, I find. That's kind of a matter of preference here. All right, and last thing is that if you have to salvage some data from IDL, there is a scipy.io.readsave function. This was originally a IDL save module that by Tom Robitaille, who is maybe the most prolific astronomy Python person that I know. He's, everywhere I look, he's doing something. But yeah, so this has been merged into scipy.io maybe like 4 years ago. And I've been lucky enough not to have to deal with IDL since then, so I was only ever using the IDL save. So it's pretty simple. This is just like to tell you it exists. You can just pass it the name of a save file, and it will fail because I didn't import it again. This is actually a file with some X-ray data that I got from Daniela as an example. But it basically returns a dictionary-like thing with all the stuff inside the file. In this case, it's just a single huge array and then a tstart, a separate attribute here. And you can do stuff like, so it has read it into a NumPy array of length 6 million or so. All right. So that's it on I/O. Yeah?
So civilized readers will uncompress, unpack, unzip, all those things on the fly. Does that work here?
I don't know.
Like Fitz Files.
Fitz.io and AstroHackWeek.
Okay.
Well, if it's gzip, not if it's it's an open source project.
OK, so yeah, the question that I didn't repeat was, can you just pass gzipped or bzipped things directly to these functions and it will take care of it? And I think the answer was, for Fitz files, yes for gzip,
Yes, for
no for bzip.
and they also both support file. So one thing I wanted to mention, if you scroll back to the top of your file of SQL there, so there is an Astro query Sci-Fi affiliated package.
Yeah.
Which will make that a lot easier. However, something that would be useful for this week, the SDSS module for Astro query does not behave like all of the other modules that API. And one thing that would be good would be to make the SDSS Astro query module.
Yeah, so the comment was this SQL query here, there's actually an Astro query package that's not part of base AstroPy, but it's one of the affiliated packages I talked about earlier that you can use to simplify this sort of thing.
But it could use some work.
Yes, but it can use some work, could be a hack. Yeah. Andrew.
Doing some big data stuff also this week. One thing I've noticed with all of the CSV readers that you mentioned is if you have really big files, it takes a really long time because what happens, I think from type checking, that takes for the checker, it has to identify specifically what the types of every column is. But if you give it some massive catalog of data, it's almost always the case. I'm not talking tens or hundreds of gigs. It's almost always the case you know that this is an int, and it ain't going to turn into a string.
Yeah, but shouldn't you not be using ASCII formats for that?
Exactly. Something's gone horribly wrong if you have gigabyte ASCII files. But it's the most common way, for example, the MIT simulation data is transferred.
Oh, really?
Convert that text file into a binary file once. They never have me use the binary file.
Oh, I understand. But I mean, what reader would I use that doesn't hang for hours on the conversion?
I use very
So that's what I do. I have my own.
Kyle, can you say a few words for posterity about why we should be using binary files and not text files?
Um, I mean, yeah, the main thing I guess is that oh yeah, sorry. So why should we be using binary files instead of text files? For small stuff, it's fine to use text files, but for big stuff, it really is like a speed issue. A lot of stuff, at least in my area of astronomy, is actually I/O limited, and it would just be crazy to store everything in ASCII.
So I disagree, even for small files. I mean, I agree with you. I would extend it to small files because whenever you write or read an ASCII file, you always are making a precision loss. Even if you write out to 16 decimal places your ASCII file, you will not be transmitting the information at full precision. And so it necessarily...
Well, no, if you write out like 19 digits, it should be complete.
There's any guarantee that conversion to ASCII and backup.
That is true. That is absolutely true.
But your measurements are given 3 digits.
Yeah, but you shouldn't be making that decision inside your code. So inside any code that might be used by somebody else.
So you're saying we should use HB5?
We should use something binary that preserves the
What are
precision
just
of the
examples of binary?
like Fitz, HDF5, just in binary.
Yeah.
Binary.
Fitz and HDF5 are the two main competitors. There's also a new format that's called ASDF that no one should be using yet.
I was just going to ask, by binary, what do you mean? Do you mean just writing out bytes?
Yeah.
Writing out bytes in some order that you decided to include in?
Well, you
No,
know,
I mean, I use these files or something, but
something with defined endianness.
Yeah.
Yeah.
I mean, so my philosophical viewpoint is if you're going to use binary, don't use unstructured formats. Because then when you change your code, you'll never be able to deal with that.
Oh, yeah,
So
that's
you
awesome.
specify, like Fitz or 85, you specify a variable name, and as you add new things, it doesn't completely break everything you've done in the past.
Maybe we need a file formats breakout at some point.
Yeah.
I'll argue over
We should
file formats.
argue about this maybe over lunch.
just very quickly repeat what they talked about, which is that floating point numbers do not behave the way you would expect them in more cases than you would think. So converting them to ASCII, where you're writing them out as something that is not a floating point number, but it's just a string of digits, and then converting them back can cause very interesting behavior that we should prevent. Yes.
Cool. Okay, so for the second part of this morning was called Exploratory Data Analysis. So I sat down and thought about, if I have some data, what can I do with it? What should I do with it? And especially in the case of exploratory data, yeah?
You're hard to hear.
Oh, can you?
Can't hear very well back
You have a mic?
You have the mic goes to
The mic goes to the camera. Okay, so I'll just have to shout?
Yeah.
Does that work better? Okay, I'm gonna try.
However, you shout, yes.
I'm gonna try shouting.
Like Occupy, we can have somebody yell at Astro.
I'm going to try shouting. So the idea of the second part was, if you have some data, what can you do with it? For example, you might be, usually maybe you collect some data with some specific research question in mind, but sometimes you might have, say, a new instrument or a new data analysis method, and suddenly you have a data set that, you just haven't maybe any big expectations for, and you just want to have a look what's in there. And so I collected some methods with which you can do this, and a lot of this is very basic, but I thought I'd put it up anyway, especially for the people who don't work that much in Python and with NumPy. In principle, there are two ways in which you can split up, your exploratory data analysis. You can split it up into a numerical part where you try to summarize your data into a bunch of numbers, and ideally those should be useful and informative numbers that tell you something about what's in your data. And then the second part is visual summaries of data, so some form of visualization, which I'm sure you all do in one form or another in your research. So I'm going to give you some intro into that as well. And again, this is also my first time doing this in an IPython notebook, so we'll see how that goes. And again, I also have some query requests, but I actually didn't only want galaxies, I also wanted stars and QSOs. And so now, you know, I have this thing where I also have lots of stars in them. So the easiest way, which I think you all know, to summarize data is just to compute the arithmetic mean. And in NumPy, that's really easy. You've already seen it in the earlier exercise. You can just call numpy.mean on it. And in this case, I forgot to say this. So what I did up here is read it into a data frame, a pandas data frame. We haven't really done pandas in this tutorial, partly because neither Kyle nor I are really experts on pandas. I know enough pandas to sort of read in data and display it prettily, but that's it. So if someone felt like doing a breakout on pandas this week, that might be a fun breakout session to do. So this data was all in a CSV file, and I just read it into a data frame, and then you can just print it like Carl showed you a bit earlier, and you get the different colors for this SDSS data set, you get the class and some other information. And so what I've done here is just get all the lines in my data frame where class equals galaxies, so these are just all galaxies. And then I took the R-band magnitude, because we're currently just looking at univariate data, and just made a NumPy array of it, and then just computed the mean. And the mean R-band magnitude of the galaxies is 16.647. If you have several okay, interesting. If you have several a multi-dimensional array, then you can, like Kyle showed you earlier with sum, you can call axis on there, and you need to make sure you call it over the right axis, because if you do it over the wrong axis, basically you don't average over the sample for each color, but you average over all colors for each galaxy, which is probably usually not what you want. And I always forget which is which. I always try them out and make sure that the shape matches, and that seems to be faster than memorizing your axis dimensions, to me at least. The mean isn't always the most useful number. Yeah?
Can you comment on the difference between NumPy mean and NumPy average? Is there any difference?
It's the same, except average takes a weights argument, so if you need to do a weighted average, then use that. Otherwise, I think they're the same.
Okay, the question was the difference between NumPy mean and NumPy average, and average uses a weight argument. So that can be useful for weighted averages. The mean isn't always the most useful thing to do on your data if you have a very skewed distribution. So one other useful measure that you can use is the median, which is just the middle of your sample. And again, there is a function in NumPy median, which will compute the median of the R-band magnitude. And you can see, 16.761 is not the same as 16.647. So it's, they're not equal. And then, so this is what I wanted to tell you here is, if you have a symmetric distribution and you have a big sample, then the mean and the median will be equal. If your distribution is asymmetric, it won't be, because the mean is much more affected by outliers. The third thing that you can do, which you often want, is to try and figure out what the maximum of this distribution is. And that's a bit more tricky. That's not just a nice NumPy function that you can plug in and say, what's the mode of my distribution, which is the maximum. The simplest way, which will probably make a lot of people in this room cringe, is you can just compute the histogram of your your sample, and you can set a number of bins in your histogram. And you have to be very careful with this, because your result will depend on the number of bins, which is why people don't like it. And remember, this is all exploratory data analysis. This is to give you a first feeling of what's in your data. That's not probably what you should be writing in the paper at the end. You're going to learn later in the week how to do a lot of this properly, but if you just want to do something quick and dirty to learn something quick about your data, then you can do this. So I've used NumPy histogram to make a histogram here, and it gives you the edges of each bin and the number of counts in each bin. And then you can use, for example, NumPy where to figure out where the counts have their maximum. And then you can find the midpoint of the bin where this is the case, and then I set a rough estimate of my mode. So that works. So means and medians are a sort of nice way and modes are a nice way to see the center of your distribution, but you also want to know something about the spread. So this is where you can use the variance and the standard deviation. And again, I compute, NumPy var and NumPy std are the functions to do the variance and the standard deviation. Again, remember, if you have multi-dimensional data, you want to do this over the right axis. Yeah?
I'm not 100% sure, someone can overrule me, but I believe that the standard deviation and variance in NumPy are with n on the denominator, not n minus 1.
Yes, you have to set the DVOF for one of them,
If you want the other one.
Yeah.
Okay.
Okay, which one?
The comment was that the standard deviation and the variance are not 1 over n minus 1, but 1 over n, so you need to make sure to set this correctly.
It's standard deviation of 1, just one number, and it gave me 0, so I think it would have to have the 1 over n definition.
Okay, where do you set this? Do you know?
It's the keyword DVOF equals 1, so delta degrees of freedom.
Like this?
Yeah, that should be it. It's possible that variance doesn't require what the standard deviation does, or the other way around.
Okay. Well, both of them work. So, okay, one thing I want to point out here, if generally you have data sets that contain not a number, for example, that can screw up these calculations. There are functions, nn mean, nn var, and nn standard deviation, which will do it instead. So the last thing that you can then do is compute what actually the standard error on your mean is. So how well did you determine your mean? And that there's no actual NumPy function for this, so you just have to compute it by hand. And then you can see that we have pretty big samples, so the error on the mean is pretty small. Those two numbers, or those three numbers, aren't the only useful thing you can do. If you want to, because they don't tell you anything about the shape of your distribution. If you want to know a bit more about the distribution, you can compute something called quantiles, which is just the number of or the sample quantile is the fraction of the sample that's below the point that you choose for your quantile. So for example, the 0.25 quantile is the point where 25% of your sample lie below that point. Note that the 0.5 quantile is also the median, which should be obvious. Some of them are special. The 0.25, 2.5, and 0.75 quantiles are called the first, second, and third quantile. And the difference between the 0.25 and 0.75 quantiles are called the interquartile range. Remember that. It's going to come up again later. There's no NumPy function that I know of to compute quantiles, but there's in SciPy stats, there is a function mQuantiles, and that will compute it for you.
There is a NumPy that
That's a good question. I'm not sure.
That does
Actually.
that does what you're does the same thing.
It does the same thing?
Just have to
Okay.
multiply by 100.
Pardon?
You would put in 25 instead of 25, but otherwise it's the same.
Okay. That's good to know. So I learned something too. Awesome. With these, you can compute what's called a Tukey 5-number summary, which are 5 numbers that can be considered a first idea of something useful to learn about your distribution. And that's basically the first quantile, the median, the second quantile, and the minimum and the maximum of your sample. And I've just made a small function here to do this. But if you're working with a pandas data frame, as we are, Kyle showed you earlier this function describe, which you will see actually does the last 5 things here exactly what I just defined. So that makes it really, really easy. So one thing that you can do if you now have the mean of the sample, or if you've done your first description of the sample, maybe you have an idea from theoretical expectation or what your telescope knows how to do, what the mean should actually be. So then you might ask, how close is is my sample mean to the actual mean? And for that, you want to compute something, where you take the sample mean, the difference between the sample mean and your theoretical prediction, and then your standard error needs to play into this too, because your difference could just be due to the fact that you have a very spread out sample. And this is actually called the student t-statistic for univariate data. And again, this is implemented in scipy.stats. There is the scipy stats ttest _1samp, which is just for having, a theoretical prediction for your mean and your actual data. And then I just made up some value for this, and then you get a number for the t-statistic, and then you also get a p-value for how likely that t-statistic is if the null hypothesis is true, that is, that the sample mean and the theoretical prediction are the same. And for this, it's really small, so it's really unlikely that this is true. Again, I would use this with a bit of care. Particularly, it might make the Bayesians in the room cringe, but it's a nice thing to do if you just want a first idea of what's going on in your data. And then what I also want to talk about a bit more is the functionality in scipy.stats, because I think it's really useful for many cases. In particular, it has a lot of probability distributions, both discrete and continuous, implemented in scipy.stats, which you can use for various purposes. And I just want to give you a quick example of how to do this. So say you want a normal distribution. You can call scipy.stats.norm, which will define a normal distribution, and then you give it a location, which is the mean, and a scale, which is the variance of your normal distribution. And I just gave them some values. And this will make, I've just printed it out here, this will make a sort of distribution object internally to Python, or to Scipy. And that's not particularly useful in itself, but you can now do lots of stuff. You can call lots of methods on it and do lots of useful stuff with it. So for example, you can make random variables. So this is just 100 numbers picked from this distribution that I just defined. There's also, as Kyle said, some overlapping functionality in NumPy. So if you just want a quick, random normal set of random normal variables, probably NumPy .stats will be faster, or NumPy random will be faster. But if you have more stuff to do with that particular distribution, using the Scipy version can actually be really useful. Then what we can also do, for example, is just make the probability density function. So in this case, I just plot it, but you could imagine there's much more different things that you might want with the PDF at a certain location. Perhaps same thing you can do, you can plot the cumulative distribution function or just compute the cumulative distribution function at a given point should you need it for some reason. There's also mean, median, variance, and standard deviation that you can call directly on this distribution. If you ever wanted to know, I don't know, what's the, well, it's a bit stupid to do with a normal distribution, but maybe with some other distribution, you might ask, what's the standard deviation of my distribution as I define it? You can call this, and it'll come out as you expected. The mean is 2, the median is 2, and the standard deviation is 0.4, just as we, define it. If you want more of these summaries, you can call just stats on it with any combination of M, V, S, and K. So that's the mean, the variance, the skewness, and the kurtosis, and that will just give you any of these. And then, of course, the normal distribution doesn't have any skewness. Similarly, for just computing the nth order non-central moment, you can use the moment method, like this. And then, there's even more functionality if you need it. You can, Yes?
Is there a way to get the log of the density or the log of the CDF sometimes?
Yes. You can do log PDF, log CDF, and all of these.
Can you get the support of the function?
Ooh, good question. The question was whether you can get the support. I don't know offhand. I don't think you can do that easily now. Not with an inbuilt function, I don't think. Hmm?
Do question mark on it?
Doesn't have a docstring. I don't know. I will look it up during lunch. But it needs a parameter, so I don't think it's the support. For more advanced purposes, which I've used a couple of times, you can get the survival function, which is just 1 minus the CDF, or the percent point function, which is 1 divided by the CDF. And in the same way, you just put in a value or a NumPy array and compute it on that value or NumPy array. And then you can plot it or do whatever you want with it.
You can close that.
Oh, it's the confidence interval. I do know this. So this is the confidence interval sort of around your mean. It will give you the values where your confidence interval is 0.6. Yeah, the last thing I want to show you is if you have a sample and you think your sample follows that, comes from that particular distribution, you can call fit on it, and it will fit the parameters of your distribution to your sample. So here I just sampled randomly from this time with NumPy because that's what my brain automatically goes to. And this time you don't actually define your distribution first like we did earlier with parameters, because the parameters is what you want to estimate. So you just call your scipy.stats, your distribution.fit, and then you put in your data. And ideally, it should give you values close to what you put in. So this was all for continuous distributions, which basically are defined for all real values on their support. If you have there's an error. If you have a discrete distribution, they work in exactly the same way as before. So except that now you don't have a PDF, a probability density function, you have a PMF, a probability mass function, which you have to use instead. But otherwise, it's exactly the same thing. Ah. Yeah.
You can get the support by doing interval of 1. I guess. We tried.
That works. Okay, so you can get the support by doing interval of 1, which makes sense. It's the interval in which all of your probability density is located. There is a lot of distributions which I encourage you to look at. Basically, almost everything that you might want to, every distribution you might think of is probably in there. I've put this exercise here. I would rather not do this now because we're a bit pressed for time. So I'm going to leave that for you to do at your own leisure if you feel like it. But it's there. So far all we've done was on univariate data. So just one, except for the means and variances. What if your data isn't univariate? You can, for example, if you now want to look at how your different dimensions vary with each other, you can compute the covariance between them just by calling numpy.cov. And I put this into the wrong format to do this between the three. My numpy array is the wrong way around for numpy.cov, so I just called the transpose on it, so it's now between the 3 columns, as it should be. This matrix is symmetric about the diagonal, and they should be and they should be just the same as the mean, I think, except for that factor before. If you're not happy with the covariance, but you actually want to compute the correlation coefficient between 2 samples, that's just the ratio of the sample covariance divided by the individual standard deviation. There's a NumPy function to do this. It's called it's this, and again I did this the wrong way around. Obviously the correlation coefficient between the data and itself should be 1. They should be exactly equal, but that might not be true for others. They should also be 1 if they're exactly the same except for some kind of scaling offset. We can also test whether the means of the 2 samples are comparable. With that, we can use a generalization for a student's Ttest for higher dimensions.
Just a note before, the diagonal was not exactly equal to the variance, and that's because you needed to include the DDOF equals 1.
Yes, I think so. Yes. Yeah, so now they're equal. Cool, thank you. Okay, so you can compare the means of 2 samples by just doing the generalization of the student's Ttest. And this is also in scipy.stats, and that's Ttest_int. And here I just do it on 2 of my magnitudes, U and G. And it gives you an object, a sort of Scifi stats object, which has 2 attributes, statistic and p-value, like we saw above. And then you can just print them, and it will give you the t statistic and the p-value. And in this case, the p-value is so small that it defaults to 0. So the means are not really compatible between the U and G band magnitudes, which isn't very surprising. The other thing that astronomers often do, I'm just going to go through this a bit quickly, is the Ttest. And again, in Scifi, you can use Scifi stats.Ktest to compare your sample to some distribution, some theoretical distribution. And this will take sort of all the standard Scifi distributions in here, which is kind of useful. So you can plug in your distribution here, and then it just compares the 2. Or you can compare 2 samples with the 2-sample Ttest, and that just works in the same thing. And both of these again have this kind of object where you can read out the statistic and the p-value. And I think that's new in one of the more recent versions of Scifi, so be careful if you work with one of the older ones. The other thing I find really useful that astronomers often do, and that is really useful in Scifi, is some kind of optimization. So I just wanted to quickly show you how to do that. If you just want to fit a function, and in this case, I just have a straight line, and you're pretty sure that the errors on your data are Gaussian, you can define just a straight line function, and you can use curve fit in scipy.optimize, which has all the optimization stuff, to fit your function to some data, and that basically does weighted least squares regression. So in this case, I'm going to compute this for the R and the Y G-band magnitudes, and I just read them into 2 variables, x and y. And you put in your function definition first, your x data and your y data, and then you can put in some initial guesses from your variables, but you don't have to. And this again returns this returns basically the best fit parameters and the covariance of those, and then again you can just print them. And then we can also plot this. If you have some kind of error, I just made some errors on the G-band magnitudes, I just made them up here. Then you can put them in as well, and note that because this does weighted least squares, those errors don't need to be identical and independently. They need to be independent, but they don't need to be identically distributed. So that's useful. And again, as you can see here, I have these error bars, and these error bars are not the same for all the data points. And it fits the straight line by taking into account the data points. So this works if your errors are Gaussian. If your errors are not Gaussian, you run into a bit more trouble, and you need to define your own sort of likelihood. And I think if you don't know what a likelihood is, you'll learn more about this later this week, I hope. I just defined one here. I just set up a class that will compute the likelihood. In this case, it's the Poisson likelihood, because I just happen to work a lot with Poisson data. And then you can define an object of this Poisson likelihood that I defined with your x and y data in your function, and then you just compute the log likelihood of these parameters that you just put in. And if you actually want to do your regression, what you can then do is you can put it into scipy optimize.minimize, and that's basically a wrapper for lots of different minimization routines implemented in Scifi. And which ones you should use depends in detail on your problem, and I'm absolutely not an expert on this, but BFGS seems to in general work quite well. So if someone has more expertise, they might want to pick whatever is optimal for their problem. And then again, this will actually output an object now, like this, which has these different attributes which you can then look at in detail. You can ask whether the optimization was successful, what the best fit parameters are, what the likelihood is of those best fit parameters. And that's sort of all for the numerical summaries that I wanted to show you. This was just a really brief overview over some functionality that might be useful for your exploratory data analysis. Do you have any questions about this part? Okay, cool. So then I want to go on to the second part, which are the visual summaries. I think all of you in your daily life make figures. This can actually go away because I did that. So, numerical summaries are great, but our brain is really good at seeing patterns and at actually parsing what kind of structure might be in your data. So I think probably all of you in your research always plot data at some point, but in exploratory data analysis, this is a really powerful tool to do. So just quickly, for those of you who are not, Python people, in the notebooks, you can use this notebook magic function, which will just make plots appear in the notebook. And then you can import pyplot from matplotlib, which was one of the major plotting packages for Python. There are others, some of which are built on matplotlib, one of which I will show you in a little while. But this is sort of one of the standards that you can use. I still find it very confusing because everything you can do in matplotlib, you can always do in several ways. And it's not always clear that they all work in the same way. So some of this is a bit confusing, and I might be plotting things differently than you would usually do this. That's fine. So the simplest thing that you can do is, let's just make a line plot, and you can just call plot onto bits of data, and then you can give it some labels, and you can give it some limits. And if you do this, you just get, a sine curve. This function, pyplot.plot, makes a plot, and it does a lot of magic in the background. Some of the magic we can do ourselves, and sometimes that can be useful if we want a higher level of degree of control over our plot. So in this case, what I did is I actually did it in a bit more Pythonic way by making an object, a figure object, and then I added some axes objects to that figure object. And in these axes object, that's usually stuff that Python does in the background, and we can now call plot on this and do it in similar ways. Notice that this syntax has changed from just calling pyplot directly. But this can be useful if you need some higher level of control over your plots. What I would really like to do, because I think it's really useful, is adding in Seaborn, because Seaborn has a lot of functionality that if you want to do more complicated plots that sometimes can be a pain to produce in matplotlib, but can be really simple to do in Seaborn. So I'm just going to import Seaborn. At the very basic level, Seaborn actually changes your standard output for matplotlib. And as you can see, our plot has changed. It's now got a gray background. And the color scheme has changed as well. You can change some of these things by using this command setStyle, which just changes it for your whole session. So if I choose, for example, white grid, it will, ideally, I can just plot this again. It now still plotted a grid, but it's now white in the background. So with this, you can sort of, on a high level, control what's ongoing in your plot. You can also use width if you just want one plot that has a different style. You can just use width and then put your plot, and that will just change it for one plot. I encourage you to just play around with this sometime and figure out which ones you like and which ones you think look best. I should also say that you can set different contexts based on whether you plot for a paper, for a presentation, for something else. And with this, it will change things like the font size and stuff. You can also manually change the font size if you want it. I usually find it a bit small, so I usually increase the font size. And that will change what your plot looks like on a higher level. I want to make a note about color, because color is a really important part of your visualization. And I don't know how many of you think about what kind of color palette you choose when you plot. And this is a really important decision to make, because depending on what color palette you choose, you might either find spurious things in your visualization, or you might miss features that aren't there, or especially things that might look on a screen might look awful in grayscale. For example, the standard jet scale, that palette that I think Matplotlib doesn't use anymore. In the next version they won't use it anymore. But if you plot that in black and white, it will come out horribly. It won't look any way the way you want it. And there are many introductions about this on the web. I put 2 of them here for you. And Seaborn has a lot of functionalities to help you play around with color palettes. I like in particular this one because then colorblind people can see my plots too, I hope. Although I suspect that also again depends on the screen and your printer. I'm not sure. And you can set your standard color palette with set palette for your session or for your script or whatever. Okay, so that was just sort of generally a few remarks on plotting. So now let's add some astronomy data. That's the same thing I did before. And again, I'm just going to read in the data frame. If you want to visualize univariate data, as we said earlier, the easiest thing that you can just do for continuous data is make a histogram. So we can call this function hist, which is a matplotlib function on your axes object, and it will make a histogram. You can change the bins here. If you set norm equals true, it will make sure that the integral or the sum of this sums up to 1. You can set the range in which your histogram like this. You can just try, if you want to cut off bits, you can cut off bits. You can also just set the edges manually, in which case they come out looking funky. The problem with histograms is that what it will look like depends strongly on how fine-grained you choose your binning. And if it's too coarse, you might just miss some features. Or if it's too fine, your noise might hide some overall structure. So let me show this to you. Here's a histogram where I just picked 20 bins. And I added another normal component to this. And this just looks like the plot we had earlier, right? So if I now make these 200 bins, suddenly this additional feature that I added in artificially pops out. And so this is a problem. This is one of the reasons why people don't like histograms much. So you can, try this out and figure out how many bins you need to actually do this. There is no really all that good a priori answer what the right bin size should be. One of the methods that you can use is to make variable bin sizes that will decide it for you. Is use Bayesian blocks, which is a sort of iterative procedure to determine how many blocks you should have in your histogram. And this particular implementation I stole from Jakes van der Plas's blog. There's also a version in AstroML if you're interested in that sort of thing. And that's just his code, which is just a function. You can compute now just the bin edges, and then you put these edges into your histogram function, and it will make this for the data that we had earlier. And you can see that the galaxy data looks quite funky in this. So that's one way to visualize univariate data. Another way you can do this is with something called a rug plot, which I don't think many of us use very often, but I thought I'd show it. That's just basically a plot which just shows your individual data points on the axis as just a little line. And if you have many of them, they kind of look like a rug, which is why it's called a rug plot. In straight matplotlib, you can use this function vlines, which just makes vertical lines of some form or another, and just plot them. If you have Seaborn, Seaborn has an inbuilt command to do that. So this is the Seaborn command. For the other thing that you can do on your univariate data, if you're unhappy with your histograms, is make something called a kernel density estimate, which I think some people here infinitely prefer to histograms. And a kernel density estimate is basically what you do is you decide on a kernel and you put it on the point where your data is, and then you sum them all up for all your data points. So it's basically this linear sum of lots of kernel functions that will sort of approximate the distribution that you're interested in. So basically you have to think about, you take your data point, and instead of your data point, you put in a function, say a Gaussian. You could put a Gaussian with the mean of that location. And then you do that for all your data points, and you sum them all up, and then you normalize them. And that's an estimate of what your probability distribution might look like. Again, you have a kind of choice of a scale parameter in there, and the sort of same caution applied to some extent, that if you have a scale parameter that's too broad, so if you just add up lots of really broad Gaussians, then that distribution will look really broad. If they're really, really narrow, you might end up just showing lots of noise features. And there are some rules of thumb that you can use, and in scipy.stats you can use the Gaussian KDE function to compute the kernel density estimate, and you can choose one of these rules of thumb, which have, I think, different underlying assumptions. So you should be careful with that. And here's an example of actually doing a plot. So I define just the kernel density estimate for these galaxy data set. And then I just set an x coordinate to plot on which to compute your kernel density estimate. And then you just do the KDE at these positions, and then you just do a plot. And then here I just do a rug plot, and on top of that I plot this kernel density estimate. And this is what it looks like for the galaxy data.
Does this smear out your distribution in the KDE?
Yeah, I mean it's a kind of smoothing technique to some extent.
It's biased towards, it will bias you wider, right? Or no?
I guess that depends on the scale that you pick. Right. Yeah.
Not quite, because each one is centered on the data point. So you could choose a kernel, but it's not the top hat. You have to pick a kernel which is at discrete chunks of the data. So you can do a histogram as a density estimate, but just choosing the top hat will give you a histogram which has much more steps in it than a regular histogram, because there'll be one step for a bunch of data.
But if you sample that at the bin centers, you would get a histogram back.
Okay. So you have to do this kind of all this code in matplotlib to make it happen and use Scifi. Again, in sort of Seaborn, you have this function KDE plot, which will just sort of plot this, and you can choose whether you want to shade the region underneath or not. That's up to you. Also in Seaborn, you can combine all three. You can make, wait, let's put this. Oh, that was a bad idea. Oh yeah, there we go. You can make, if you really want to, you can make a rug plot, a histogram, and the kernel density estimate all in one plot. But depending on what your purpose is, that may be a bit of overkill. And there's another Seaborn function called distplot, which is similar, which has a lot of functionality in it. And in that, you can also, as we did earlier in Scifi, you can fit one of the Scifi functions or another distribution to it. So if we imagine that our galaxy sample was Gaussian, I just fit a normal distribution. Obviously, it doesn't work very well. But in theory, you can fit distributions to this if you really want to and get a first idea of what that looks like.
Does it give you the parameters?
Possibly. I'm not sure, actually. I'm not sure. I have to find out. Probably. I wouldn't be surprised if it didn't somewhere. So that's what you can do if you have sort of univariate continuous data. But we can also play around with categorical or discrete data, which doesn't necessarily follow a statistical distribution, but we might want to visualize it too. In this case, we can do something that looks a bit similar to histogram, but actually isn't. It's a bar plot, and for this, we can't choose the number of bins. They'll just be the number of categories that we have. And in this case, I just used discrete distribution, the Poisson distribution, to make some data. And then you count all the different occurrences of each integer number to make the counts. And then you can plot this as a bar plot using the pyplot function bar. In this case, I also added some error just for visualization, which isn't true. It's just a number. Just so you can see it, you can also plot error bars on top of this kind of plot. Here we're going to now do just in our sample, as this is the reason why I didn't only pick galaxies, but also had stars and quasars in our sample. I'm just counting all the numbers of galaxies, stars, and quasars. I'm sure there's a better way to do this in pandas. I just don't know enough pandas to tell you. And these are just the numbers of stars and quasars and galaxies. And again, you can now make a bar plot with these numbers, and then set the ticks so that they read galaxies, stars, and then I actually need to run this code. So now you've got the relative numbers of the different types of objects in one plot. Again, you might want to think about, so this is all for univariate data, and univariate data is great because it's really easy. You have a two-dimensional interface, your screen or a paper or whatever, and for this one dimension, it works really well. If your data is multidimensional, you need to do a bit more work, and here's really where Seaborn becomes really handy. However, I should also warn you that Seaborn relies a lot on pandas, so you might want to at least have some basic familiarity with how things work in pandas to make all these complicated plots. The easiest way, which I'm sure we've all done before, is to just make a scatter plot. And scatter plot can be really useful. You already see a lot from this. However, if your data set is really big, then your scatter plot might not be a useful thing to do, because now you've got this sort of indiscriminate blob here, and it still sort of shows the overall structure, the overall sort of trends, but if you have any structure in here, you won't see it because it's this indiscriminate blob of many points. So what you might want to use in this case is just a 2D histogram, and in Matplotlib there's this hist2d which works in the same way. You can define some bins, you can define a range, you can define a color map, and then you get a 2D histogram like this. And here you can see that there's a bit more fine-grained structure that you can read out. I personally actually like this function better. It's called hexspin. All it does is put this on a hexagonal grid. Whoa. Oh, there you go. And I just find this a bit prettier to look at. But that's, I think, a matter of sort of preference. Notice that unlike histogram, they decided to name this grid size and not bins. So be careful. I always get this wrong, so I always get errors with the wrong keyword that I put in. If we want something more complex than that, and if we also want to plot the histograms of your two individual distributions, you can fiddle around with Matplotlib, or again, you can call the Seaborn function. And in this case, it's the Seaborn function joint plot. And this is now a bit more complicated. So this is your first variable. This is your second variable. These are just the U and G magnitude, or the R and I magnitude, I forget. Again, I make a hex plot here. I set some limits. And in these two keywords, you can set individual keywords that will be passed on to Matplotlib. So in this case, it's the hexspin function, and in this case, it's just the histogram function. And that allows you some control. And here, you now have the same kind of hexspin plot with two distributions, the two marginal distributions on either side of it. So that can give you also some overview over what the different variables look like. We can also, again, do density estimation. In this case, I do density estimation on fewer data points because otherwise it would take us a long time. It's a bit more involved in Matplotlib because, again, you need to call scipy.stats Gaussian KD, which also works on multidimensional data sets. And then you get this. And for a reason I have never understood, this decided to sort of flip on the side. And I'm not entirely sure why it does this. This is probably some weird way I've laid out the arrays that I don't quite understand. Yeah.
So you always put the origin equal lower, because otherwise 0 is a default.
Like this?
Yep. And then probably then translate or transport or something.
Haha.
Usually you try until you get to
Yeah. This is usually good advice from Matplotlib. You fiddle around until it works. Again, you can do a 2D KDE plot as we did above for one dimension. You can shade it, for example. Then it will look like this, or you can just print the outlines and you get a kind of contour plot. And that works in joint plot too. Instead of hex as we did above, we can now do KDE, and then you get kernel density estimates on both sides, which make for quite a nice plot without too much effort on your part.
If I could say one thing, actually, back, for the hex skin, you want to actually see where you're imaging the pointer, there's an in-out particle, which is really helpful so that, the first hex skin plot, so min, c, and p, and that will make the color map. Invert your color map, so a color map that
Cool.
So could you just change it to 10, just to see what this, but then we're not going to see the small bit. The small bits will disappear.
Yep.
Yeah.
So this is 2D though.
So you're hiding, you can hide data in your
And you can hide your files.
Yeah,
Cool.
good option.
So if you have even more dimensions, then you quickly run out of dimensions to plot your figure in, just because your screen happens to be 2-dimensionals. You can do 3D projections, but then many data sets have even more dimensions, so that's not too useful. So I'm not going to talk about 3D projections today, but there are a few things you can do. And this time I'm going to start with categorical data for a change. So bar plots are kind of useful if all you have is a number of instances per category. Like you have 1,000 galaxies and you have 500 stars. But what if for each galaxy you have magnitudes like we do? Then this will be now mostly Seaborn because that's where a lot of the functionality just resides. That makes it really easy. All of this you can do in plain matplotlib. It just takes you a lot of fiddling around. And so the first thing that you can do is a kind of categorical scatter plot. And here I now use the integration with the pandas data frame. I'm just going to put the data frame with the galaxy and the stars and so on here. And then I'm going to tell it on the x-axis plot the class, and on the y-axis plot the R magnitude. And this will then look like this. So you get you get galaxy, stars, and QSOs, and this is sort of just spread out for a bit of visualization, the distribution in this direction. Again, because we have a lot of data, this might not be the most useful way to plot this. Instead, we can make something called a box plot in exactly the same way. And what this will now show you is the median in the middle, the interquartile range that we defined earlier, and then these whiskers here are just 1.5 times the interquartile range, and everything that's outside of this will be just plotted as dots as outliers. So this is a really nifty way to see where most of your distribution lies and where your outliers lie. And so it's much easier to compare this kind of plot to each other than it is to compare that kind of plot, to compare things in this kind of plot. If you want even more information, you can do a violin plot. And this basically just shows you the distribution like this, plot in this dimension for the different classes. And that gives you even more information. And again, in the middle, the white dot is the median, and this is the interquartile range, the sort of more broader line in there.
Double the amount of information we need now.
Pardon?
I mean, there's a left and right duplication of this.
Yes, but if you have another, if you have another categorical variable, you can now add variables to this. For example, in this case, I added a column to our data frame called aliens, and that just decides whether a particular star or galaxy has green or blue aliens. And then now you can put hue, you can put this keyword aliens that we just add it, and this will now split this into green and blue aliens. And in this case, because I just randomly chose, these distributions will look very similar because they're basically just 1/2 is green, 1/2 is blue. But if these are actual variables, then these violin plots can look very different. And that sort of allows you to add another variable to this.
So we can use the color of a galaxy to find aliens. I'm confused. Did you specify the colors that I'm seeing? Or are they
No, they're just there by chance. But you can specify the colors. I would have to look up exactly what the syntax is, but that was just chance. So again, yeah, you see the interquartile range here and the median. If you have even more complicated data sets, you can now imagine you have even more variables that you're interested in. You can use something called a facet grid, where you basically say, just split up what I have into different plots. And in this case, I split it up into the different classes of objects. And then the other categorical variable, again, is aliens. And then for each of these, I make a box plot for the R-band magnitude. And so, again, this allows you to compare different categorical variables very easily. If you have continuous variables, you can do something similar. You can make a series of scatter plots. Again, this requires, I wrote this in Matplotlib once, and it used a lot of lines. You can use pair plot in Seaborn. And here I just use the U, G, and R band magnitudes and say make a scatter plot. And so here it plots, the histograms of the U, G, and R magnitudes, and scatter plots of U minus G, of U and G, and U and R, and so on. And these should be the same because they're the same variables, just flipped around. You can also, like earlier, you can add grids. You can add kernel density estimates, for example. And this takes a bit longer, but now you have a kernel density estimate on the diagonal and a kernel density estimate here, and this one is still just a scatter plot to show you some stuff. Finally, as a really short head up, probably for Wednesday, the other thing that you can do if you have many dimensions, you can try to reduce your dimensions to 2. And one thing that you can learn, all of this is implemented now in scikit-learn, which you will learn a lot about on Wednesday. And here's sort of 2 examples. One of this is principal component analysis, which I've just implemented here. And ideally, if your data set has really different categories, and the categories are really different in their variables, then ideally this should look distinct, but here it doesn't particularly look very, it's not necessarily a good idea for that particular data set. The other thing that I want to show you, which can be useful, is something called T-distributed stochastic neighbor embedding, TSNE, which I suspect Andy will talk about on Wednesday too. And that you can do in a similar way, that's in scikit-learn in the manifold package. Again, I use a smaller one, because a small data set, because it uses some computational power. And then you just fit and transform your data into 2 dimensions. And plot this here, and that makes sort of funky plots. This is my overview over the visualization part. I just wanted to give you a basic idea of the kind of things that you can do that might be useful to do if you have a new data set. I like Seaborn because it makes it really easy to make quite complex plots and quite visually useful plots, but it does require some fiddling around with integration with pandas. And also, if you want to customize bits of your plots, like the individual components of some of these grids, then that can require some more fiddling around with too. I think we need to stop here. I did put in 2 exercises for you to look at if you want to, and just play around with it. The first is just take the SDSS data above and just play around with it and see what kind of information you can get out of it. If you're bored with astronomy, I wanted to suggest to you to just play with this data set from data.gov, which is all the baby names from the Social Security card applications by state since 1910. And that's really a fun data set to play with, because you can, it's really easy to read into a data frame. And that won't work, I think, because Kyle doesn't have the data.
I did download it, I just didn't change the...
Oh, okay. And then you can, for example, pick in all the data for all people here named Lucy, and then you can count them. And you can, for example, make a time series, and you can try to look for correlations between different names. And it's a lot of fun to play with. So I invite you to try that out. And that's all I have. If you have any questions. No questions? Okay.
And thank you to Daniela for giving up her laptop for the entire morning session all week to run the live stream and having to deal with my Linux
Made a
machine.
lot more sacrifices than that.
That's the one that hurts worst. Okay, then I'm going to hand over to Phil, who's the master of hacking. And he's going to give a few, I don't know. You just say what you want to say.
What time is lunch?
Soon, but we can just push it back by 10 minutes.
Okay, all right.
And make ourselves really unpopular on the first day.
You're all like 10 minutes, right?
Hey David, how are you doing?
How are things?
Doing well. I'm just a bit jet lagged. Otherwise, I'm fine.